Now, I hope that you can't wait to calculate the mean squared error. From the previous cell up here, we already know what the lowest cost theta 0 and theta 1 parameters are for our regression. And this is thanks to the scikit-learn package. But let's work out what the mean squared error actually is for these two values. And for that, we're going to need our estimated y values. Looking at our equation up here, we need to calculate our y hat. What's this y hat equal to? Well, our y hat is going to be equal to theta 0 plus theta 1 times x. This is the equation that underlies our linear regression in this case. Our y hat is based on the intercept plus the slope times our x values. Let's translate that to Python code. So I'm going to create a variable called y underscore hat, and I'm going to set it equal to our theta 0 value, which was this one here. I'm going to copy this, come down here, paste it in, add a plus sign, take the theta 1 value, copy it, paste it in, and then write times x underscore 5. This, after all, are all the x's in our data set. And that way we can calculate all the predicted values in our data set. Let's print these out for good measure. So I'm going to say print, and then the string estimated values y underscore hat are colon, comma, y underscore hat. Let me hit Shift Enter, and let's see what these look like. So here they are. These are all the predicted values. Now, one thing that you can do is, if you don't want this first value here on the same line as your string, what you can do is you can come in here where the string is and insert a special character, the new line character. So that's backslash and then n. And when I hit Shift Enter now, that 0.969 will move to a new line. Backslash n is like a special character for hitting return on your keyboard. So how do these predicted values compare to our actual values? Let's print those out as well. So I'm going to say print and then write in comparison, the actual y values are backslash n, comma, y underscore 5. These are our actual values. So there we go. Ideally, we want these estimated values to be as close to these actual values as possible. And looking at this, they're actually not too far off. This is not too bad, given this theta 0 and this theta 1. So now that we know how to calculate our y hat values, let's work out the mean squared error of the regression. And I think this actually makes a really good challenge. So can you write a Python function that takes two inputs, y and y hat, and returns the mean squared error? And after you've done that, after you've written this MSE function, can you call this function and print out the mean squared error with the y hat calculated above? So feed in this y hat value into your MSE function and print out what the mean squared error is. Now remember, the mean squared error equation looks like this. We've got that formula in LaTeX notation, so all you need to do is translate it into Python code and look up what code to use for that pesky summation symbol right here. I'll give you a few seconds to pause the video and try this on your own. All right, ready? So I hope you figured this out. Now, in terms of the solution, I'm not just going to show you one solution. I'm going to show you 3 different ways that you can implement this, because there's actually many ways you can skin a cat, as they say. So while you had the video paused and were solving the challenge, I was busy looking up possible uses for all that cat skin. And the best one I came across was a Japanese instrument called shamisen. Apparently, the drum on this banjo was actually traditionally made from cat skin. So there's your random fact of the day. If you've come across any other uses, do let me know in the comments section. The Python code that you will have written will probably look something like this. You can have def, MSE, and then for the parameters, you'll have y and say y hat, colon, and the first possible approach would look something like this. You might have a variable, say call it MSE calc, and that would have been equal to 1 divided by 7, because we've got 7 data points, and you multiply that by the sum. This is an inbuilt Python function, sum parentheses, and then inside the sum you'll have another set of parentheses, and there you'll have y minus y underscore hat to the power of 2, so times 2. And because this function needs an output, you would return the results of your calculation, so MSE underscore calc. And this is one possible way to do it. Let me call this function and print out the mean squared error of y hat that we calculated. So that'll be MSE y underscore 5, because these are the actual y values, and then I'll supply y hat that we calculated a few cells above. And let me hit Shift Enter and see what we get. We get 0.95 approximately. Now, there's one improvement that we can make to this function. So this 1 divided by 7 will probably be bothering you a little bit because it's hard-coded and it would only work or calculate the mean squared error correctly if we had 7 data points. If we had 8 or 9, then the mean squared error formula wouldn't be apt anymore, wouldn't be correct anymore with this Python code. So I'm going to comment this out, but I'm going to copy it, paste it below, and what I'm going to do is I'm going to replace this 1 divided by 7 with some different code. I'm going to say 1 divided by y dot size. Y dot size will return the length or the number of samples that are fed into the placeholder for our y values. So this will also work. Let me hit Shift Enter on this cell and the one below to prove just that. Writing the code this way makes the MSE function much more general because it figures out the number of samples inside of the function. It doesn't have to be supplied as an extra parameter, and it's not hard-coded in the instructions themselves. So this is already quite nice, but there's another way you could have done this as well. Maybe you did a bit of Googling and you figured out that NumPy actually has a function called average. And this does both the summation and the dividing by the number of samples for us. So let's see what this would look like. This would be mse.calc is equal to np dot average, parentheses, and then it needs two things. It needs the function itself that it's averaging, and if it should be averaging the rows, the columns, or the whole thing. So first things first, the function it's averaging would be y minus y underscore hat to the power of 2. And the way to tell it whether it should average the rows or the columns would be by supplying the axis argument. So axis equals 0 sums up the rows instead of both the rows and the columns, which is not what we want. So if I hit Shift Enter on this and then run the cell below again, we can see that this works as well. But just because we've printed out a mean squared error in this cell here doesn't mean it's correct. So let's check it against an inbuilt function from scikit-learn. So let me wrap this in a print statement. Right, print, and then the string manually calculated MSE is colon, and then we have our MSE function in here. To use the inbuilt function the inbuilt mean squared error function from scikit-learn, we're going to have to import it. We're going to have to scroll to the very top, and then here we're going to add another import statement. We're going to say from sklearn dot metrics, lowercase, import mean underscore squared underscore error. Sorry. I hope you're not too upset and will forgive me that I made you do all this work, even though there is an inbuilt function for this already. Let's call this mean squared error function with both our manually calculated y hat as well as from the output of the regression directly. So where we were adding our print statement, let's add another one. Let's add print MSE regression using manual calc is, and then comma, mean underscore squared underscore error, and then we'll supply two inputs, y underscore 5, our actual y values, and y underscore hat, which we've calculated above, just here. And now let me copy this line and paste it below. And this one will read MSE regression is mean squared error, and instead of our manually calculated one, we can use regger.predict parentheses x underscore 5. And when we hit Shift Enter, we see that indeed all the outputs agree with one another. Our manually calculated mean squared error is the same as what we get from the machine learning package. So we've dissected and implemented this cost function correctly. Brilliant. Now it's time to plot our cost function and visualize it. We'll do that in the next lesson. I'll see you there.